Hello, and welcome to the Math Mentorship Program. Today we're going to start by looking at the basics of mathematical logic. So in particular, we'll talk about mathematical statements, truth tables, and these underlined words here. We're going to discuss their precise definitions in mathematics. So to start, I'm going to define what a mathematical statement is. And this is just any sort of statement that is either true or false. So in other words, it just has to have what we call a truth value. It doesn't have to be true all the time. All these things here are examples of mathematical statements, right? We can verify that they're true or false. On the other hand, this one over here, x is greater than 3, this is not a mathematical statement. This is called a predicate. And the reason why it's not a statement is because we don't know what x is. It could be a mathematical statement if we define what x was. For example, let x be 5. Then this would be a mathematical statement. It would be true. So it may have a truth value, but that would depend on an instance, which is x. So we call x here an instance. So it depends on the instance. And another example that may be a mathematical statement, but as is right now is not, is this one, the rock is heavy. Now, you could argue that this thing may have a truth value. It could be either true or it could be false. But there are a lot of unknowns here. Like, what does heavy mean to you? How big is your rock? And without these things properly defined, we can't actually assign a truth value to this. And we really want to avoid things like this in math. And so that last case really emphasizes how precisely we need to define everything in math. If we can't even verify that something is true or false factually, then it is irrelevant. So with that being said, let's look on some notation. From now on, we will sort of abbreviate our statements by giving them names. So usually we'll use the letters P and Q. So for example, I might say P is equal to the statement that dogs have fur. Right? So whenever I say P, I mean this thing is I mean this thing, right? Now again, this is a mathematical statement. It's either true or it's not true. And I could do similarly for Q, but I'm not going to bother. Maybe cats have fur. Okay. We may also use letters for instances, and this is where it gets a little bit confusing. For the rest of this talk, we won't really talk about instances and these variables, but if P of x was the sort of predicate, x is greater than 2, right? Or we could rewrite this as x is greater than 2 with the symbols. Then we would have a situation that we had in the beginning where we had a predicate. So this on its own is not a mathematical statement, but once we substitute in a value for x, this is a statement. And I've especially written this to sort of remind you of your functions, because this is essentially what it does. It takes in x and it tests whether it's greater than 2, and then we determine whether this is a mathematical statement or not. Okay. Now we're going to talk about truth tables. So these things are fundamentally based on something called the law of bivalence. This is by Leibniz, who is a great mathematician of the, I think, 17th century or 18th century. And he says that every judgment is either true or false, which is pretty reasonable, especially based on the definition of mathematical statement that we had before. But what this essentially allows us to do is that we can tabulate the possibilities of an unverified statement, and then we can use the truth table, which I'm going to show you in a minute, to verify its validity. And just some quick definitions here. If we have a statement that is always true, then it is called a tautology. And if we have a statement that is always false, it is called a contradiction. So now is where we're going to start looking at these logical connectives that I discussed at the beginning. And we're going to see how they connect to these logical statements that we were discussing earlier. When I say and, right, that implies that I want both things, the thing before the and the thing after the and, to be true. We will often use this symbol, this up arrow, to indicate and. And so what we can do is, and this is what a truth table is, we really just list out all the possibilities for P and Q. So what could P and Q possibly be? Well, P could be true and then Q could also be true. Or P could be true and Q could be false. And P could be false or Q could be true, and so on, right? And this is a setup that's going to pop up very often throughout today's talk. What P and Q tests is whether both P and Q are true, right? If that's the case, then the statement P and Q is also true. So to be a little bit less abstract, let's suppose that P is dogs have fur. and ignoring the little semantics for now and the little details, we will also assume that both of these things are true, right? Then the statement that dogs have fur and cats have fur is obviously true, assuming both of these things individually are true, right? On the other hand, if either one of them was false, for example, let's say there was such a cat that did not have fur, I think that such a cat does exist actually, then this statement would no longer be true. So this really tests whether both instances, P and Q, are true. Okay? Similarly, we have OR, and we're going to use something called an inclusive OR, right? So the best way I like to explain this one is this. Let's say I'm inviting you to my party, and I want you to bring some food. And I say, I want pepperoni or cheese pizza. Am I going to be mad if you bring me both pepperoni and cheese pizza? No, more the merrier. So what we want to say here is that P or Q means either P is true, or Q is true, or both are true. So to fill out our truth table, remember the setup is essentially the same as before, because we're just taking possibilities for P and Q. We don't know what P and Q are. Then the statement P or Q is going to be true when both of them are true, or when one of them is true, right? So just to, again, illustrate, let P be the statement, bring pepperoni pizza. And let Q be the statement, bring cheese pizza. Okay? Then if you bring me both pepperoni and cheese, you've satisfied my request to bring either or, right? So bring P or Q. So bring pepperoni or cheese, right? And if you just bring pepperoni, that's fine too, right? That's good. And if you just bring cheese, that's also good. But if you don't bring either, you bring me a veggie pizza, I'm not going to be very happy. So that's why P or Q is going to be false. Okay? This is where it starts to get a bit hairy. Implication. So we say P implies Q, but the symbol that we'll use is a sort of doubled body arrow. And what that really means is that assuming P, then Q is true. Okay? This is the truth table for it. I'm going to do it right now. So this is going to be true. This is going to be false, and this is true, and this is true. This may be a little concerning to you. Okay? So the reason why is because even though your statement P is false, even though the thing that you assume is false, the implication statement I'm saying is true. Why is that? So to really understand this, let's consider an example. If you do not brush your teeth, you will get cavities. So what happens if you do brush your teeth? Is the implication actually broken? And the answer is no. Well, really, you don't know. You don't know whether the implication has been broken yet. The only way to actually contradict the implication is if the hypothesis, which is your assumption, you do not brush your teeth, is true, while the conclusion, you will get cavities, is false. So in other words, this is the only way this thing could break down. Otherwise, we're just going to arbitrarily assign a true to this implication statement, right? And you can play around with this a little bit more in your head, but if you do so enough, you may come across some strange examples. So here's one. Let's say I say to you, if you damage my bike, you will have to pay for it. Fine. But then you come back with my bike, undamaged, and then I say, well, you have to pay for it. And now you're confused because I didn't damage your bike. You didn't damage my bike. What do I have to pay for? Why would I have to pay? And the issue here is that there's a disjunct between what mathematicians consider an implication and what regular people consider an implication. Okay? What's going on here is that you actually want something called an equivalence. This is probably how you interpreted that previous statement. If you damage my bike, you pay for it. If you don't damage my bike, though, you don't have to pay. Right? That's how any reasonable person would interpret that previous statement. But when we're strictly speaking about implication, then I'm right. Because if the hypothesis is false and the conclusion is true, then the implication has not been broken. I have not actually contradicted myself by making you pay, right? So this is just one little quirk about implication, and it does take quite a bit of time to get around it. However, in most practical cases, it doesn't actually matter too much. Okay. So with that being said, we're going to move on to what this means, right? This equivalence. Equivalence is exactly what you want it to be, right? What it does is that it tests whether two things are equivalent, meaning they have the same truth value. So in other words, the statement P is true or false exactly when Q is respectively true or false. So you can see in this truth table, the only time when the statement P equivalent to Q is true is when the truth values of P and Q match, right? Otherwise, it's not true, okay? The last one that we have to explore is not, and that one's simple enough. Not literally just takes your mathematical statement P and reverses it. If your statement is true, not P is false. If P is false, then not P is true. Okay. So with that background, we can actually start to prove theorems with truth tables. If you don't know what a theorem is, it's just any sort of interesting statement about mathematics. And what we've done here is we've built up enough base to be able to prove some theorems, which means using only what we know, we will be able to verify whether certain mathematical statements are true or false. That's what a proof is. It's verifying whether something is true or false, usually true. So remember at the beginning I stated Leibniz had this thing called bivalence, right? And bivalence was important because it means that a statement can either be true or false, no other possibility. And with this sort of bivalent logic system, something called the law of excluded middle is always true. And the law of excluded middle says that a statement is either true or its negation is true. So for example, let P be the statement, all lemons are yellow, right? Then what is not P? Well, it's just the negation of that. Not all lemons are yellow. And it is certainly the case that either one of these statements is true or the other one isn't, okay? So how do we prove this? Well, what we do is we build a truth table for it and then prove that this P or not P thing is a tautology. And what's amazing about this is that it's independent of what P is. For example, this statement P that I gave you, all lemons are yellow, that's just one example. I could have come up with multiple. So here, we're going to start with the cases for P. P could either be true or it could be false. But then what is not P? Well, remember, not P reverses the truth value of P. So it would be false in this case, and it would be true in this case. And then we would ask ourselves, well, what is the truth value then of P or not P? So then we look at these two things, and we say, okay, well, in this case, one of them is true, P is true. So we would say, this is true. And the second case, of course, the not P case is true, so then this is true as well. And so what we found is that in any case, so in other words, regardless whether P is true or false, P or not P is a true statement. Remember, we had a definition at the beginning called a tautology, and that's exactly what this is. You're basically looking for a column of all T's, right? That's what a tautology is. So the column is all T's, okay? And we'll continue doing this for the remainder of this video. Our next example actually comes from Aristotle. It's about it's something related to the law of excluded middle, but this is more about contradiction. This entire paragraph is a little confusing to read, honestly, but I'm going to double down on this part here that says, and it will not be possible to be and not be the same thing. And I want to know whether Aristotle is actually right in saying that, whether what he's saying is logically consistent with what we have discussed so far. So let the statement P, the symbol P, represent being something. What Aristotle has said in this statement is that it will not be possible to be and not be at be the same thing. And so we're going to test whether this is true by forming a truth table again. Again, since we only have one thing, P, right? We only need one initial column, which is P. So again, P could either be true or false. Then what is not P, right? Keeping in mind that our final goal is our final goal here is not P and not P. Okay? So not P again is false when P is true, and true when P is false. Then the statement P and not P, well, what is this? This thing has to be, it has to be the case that both P and not P are true in order for P and not P to be true. So obviously in the first row and the second row, this is not the case, because at least one of them is false. So this statement P and not P is always false. But this is good because when we negate this, right, when we flip it around, the statement not P and not P is always true. And we have our tautology again, right? So this statement is logically valid. Right? So Aristotle is right, basically, in any case. A little more of an abstract example, we're going to sort of remove all the context away, and we're just going to work with this, with these symbols. So remember that P up arrow means and P down arrow means or. And so this is saying P and Q implies P or Q. So we have to list all the possibilities for P and Q because we don't know what they are. So true, true, false, false, true, false, true, false. And if you look back to the beginning of the video, this is basically the setup that I said we would be going back to over and over again. So then when is P and Q true? Well, all you'd have to do is look back at when we were discussing the AND connective and see that the truth table looks exactly like this. On the other hand, P or Q is true when either one or both is true. And so the truth table, you can check, looks like this. Finally, we need to look at the implication. So again, when is the implication true? The implication is true exactly when both the hypothesis and the conclusion are true, or when the hypothesis is false. So if we look back at our example, we'll notice that this is always the case. Because in this first row, we have that both the hypothesis, which is P and Q, and the conclusion, P or Q, are both true. So this is true. And in every other case after, the hypothesis is false. So by the laws of implication, these are all true. And we have our tautology again, right? So this statement is also true. And if you think about it, this makes a lot of sense. Let's say P is the statement, I have a dog. And let's say Q is the statement, I have a cat. Right? Then what is P or Q saying? Right? Well, P or Q is saying, I have a dog or a cat. And this is obviously true when I have both, a dog and a cat, right? If I have both a dog and a cat, then I obviously have a dog or a cat. Okay. Our last example for today is going to be demonstrating that the negation not actually acts like a negative sign, with one little exception. So this is called De Morgan's laws, and we're actually going to see these more in the context of set theory later on. But this is essentially how it looks like. So if we say not P and Q, this is going to be logically equivalent to not P or not Q. So in other words, the little negation sign has sort of distributed over and multiplied itself by the P and the Q. The only thing that was a little different was that the AND sign changed to a minus, to an OR, right? And so you can sort of think about this like a minus sign distributing over things in brackets. Okay, but this is not something that we will focus very much on. What I'm going to do is I'm going to prove 1, and then I'm going to leave 2 as an exercise. The proof is very similar, and it involves much of the same technique. So just to illustrate, I've drawn out here the possibilities for P and Q, right? So then we're going to analyze the statement not P and Q, okay? So actually let's break it down a little bit more, just because this is our first time looking at these things. So what we can do is we can think about the statement P and Q. And P and Q, remember, is true only in that first row. Otherwise, it's false, because at least one of these things are false. Then the statement not P and Q is going to be just the negation of everything in the third column. And we're going to leave it at that. For this one, I have already filled out P, Q, not P and not Q. This is a very simple task to do. But what we're going to do now is we're going to analyze not P or not Q. So remember, when is OR satisfied? or is satisfied when either one of the sort of arguments are true, or when both of them are true. So in this case, false, false, so this is false. Here, one of them is true, so this is true. One of them is true, so this is true. And both of them are true, so again, this is true. And then finally, we can look at the equivalence. Not P and Q, equivalent to not P or not Q. Okay? And, well, if you look at these two columns, right, they look exactly the same. It's FTTT, FTTT, right? Therefore, when we do the equivalence, we're obviously going to get a column full of T's because these truth values match up every single time. And notice that in order for this to happen, it had to be the case that I wrote these two columns exactly the same way as I wrote these two columns. So you'll notice that I wrote TTFF, TTFF, and then TFTF, TFTF, right? If you mess up the order, this is obviously not going to work. Okay? So that pretty much concludes everything I wanted to say for this video. Next time and during our live sessions, we'll be going over a few more things about this, including proof methods, as well as some basic properties of functions that will be very important throughout the remainder of this program. So hopefully that was very interesting, and I'm going